Hello everyone, welcome to the fifth HFSS tutorial EC475. Today we were gonna to see how to design a microstrip patch antenna and be familiar with this kind of uh, antenna. So we will take a look at microstrip patch antenna design formula and the design parameters, uh, microstrip line properties, patch antenna properties, how it works, and patch antenna formulas, and we will see how the fringing effect. We will take a look at different fitting structure, and as a design processes, we have an example to see how to design a microstrip patch antenna. Here you can see a microstrip antenna schematic, which also commonly used to say the patch antenna instead of saying the microstrip patch antenna. It consists of one layer dielectric and two layer metal, which is perfectly conductors, and dielectric consists of the some dielectric like Rogers or uh, fiber or something like that. This is the substrate of our antenna, and we have a ground plane which is placed under the antenna, and we have a microstrip patch which is sit above the antenna. The figure you can see the width WG, which is the width of the ground plane, W which is associated with the width of the pass, L is the length of the pass, LG is the length of the ground plane, and by putting these two metal over the dielectric substrate, you can create a patch antenna. These antennas are very useful because they can be printed directly into the PCB board, and it's very common to uh, use it in mobile applications, something like that, in communication systems. It's very common to use a patch antenna, this kind of antenna, so it's good to know how it works, how it design, or maybe you can come up with a new design, a new idea, and you can use it in the future. So they are low cost, and you can design it to have a low profile and a small antenna, and as I indicated that it's easily fabricated. The patch is the yellow one, the patch metal, have a length of L, width of W, and sitting on the top of the substrate. It's a dielectric circuit board which have a thickness, let's say H, for the height of the substrate, and the permittivity of the epsilon R for our dielectric. And the thickness of the ground plane or of the microstrip is not critically important because it's a metal. By the height of the this dielectric is important, and typically is much smaller than the wavelength of the operation, but not smaller than 50% of wavelength, because if the thickness of the dielectric is so small, it's going to be so small, the efficiency of the antenna will be degraded and deteriorated. So it's not critical to uh, going below than smaller than the 5% to create your antenna. Here you can see the electromagnetic field inside or outside of the microstrip patch antenna, and as you can see, the electromagnetic field contain not only the within the microstrip line and within the substrate, but it propagates outside of this microstrip line or microstrip patch, and patch antenna you can design it to see the input impedance of 50 ohm or to create a propagation. The operation mode of this microstrip line or microstrip patch antenna is similar to a TEM, but it's not exactly TEM, but it's a COSY TEM mode. You can see the relative electrical permittivity formula, which is the effective one, because you have the bulb of the patch antenna, you have the air media, or inside the substrate you have some permittivity. So in order to calculate the electric field or radiation properties, you need to have epsilon effective, which is the effective electrical permittivity, which is equal to epsilon r plus 1 over 2 plus some small values, which is usually negligible. So effective permittivity is assumed to be epsilon r plus 1 over 2, which is usually accurate enough. There are some tools like online calculators for microstrip line or microstrip patch antenna, or you can put the permittivity, height of the substrate, and the thickness of the metal, and the frequency of operation, and you see the effective permittivity, the K, which is the propagation constant, or the W, which create the 50 ohm microstrip line for you. There are some inputs and output that you can play with them, and normally they are based on the formula and theory, and it's just some calculators that enable you to get the features of them. But also there are some applications like line calc in ADS that enable you to have a much more detail than what you see here, and I suggest you to use this line calc. If you have any question in line calc, feel free to ask me, but for the initial point, these microstrip line calculators or something online calculators is enough to design your antenna. As I said, the advantages of the microstrip antenna is it have a low cost to fabricate. It's very cheap, and it has a capability to use the conformal structures, which nowadays used in the microwave imaging and imaging application, and like satellite communication and so on. It's easy to form a large array, which is nowadays used for 5G application, which has a element spacing about a half wavelength or less. It has a lightweight weight. There are too many advantages for the microstrip patch antenna. They are very popular, but there are some disadvantages, which is this antenna has a limited bandwidth. It's usually 1 to 5%. There's some structures, there's some rules to improve your bandwidth, but it increases your complexity of designing antenna, and this antenna usually has a low power handling, so it's not good for high power antenna. You can see the figure, the H plane and the E plane of the antenna. E plane, it's aligned with the length of the antenna. If you fit in X direction, the E plane is here, as you can see in the red line, and H plane is the perpendicular to the E plane. Yeah. And for there is some rules that the length of the antenna is equal to lambda g over 2. Lambda g is the effective wavelength of the antenna and operation frequency of the antenna. Lambda naught over 2 is for the free space wavelengths, but keep in your mind that the L is equal, it's for the initial point, it's gonna be lambda g over 2. And you can see the electric field of the electric field distribution of the antenna. As you know, the patch antenna can be assumed as an open circuit transmission line. Voltage reflection coefficient will be 1 at the end of the antenna at the open port, and voltage and current are out of phase. So at the end of the patch, the voltage is at maximum, and at the start point of the patch antenna, a half wavelength away of the end of the antenna, the voltage must be at a minimum. As you can see the patch antenna, you can consider it as a capacitive antenna or as a capacitor which has a fringing effect around this metal. So if you wanted to see the effective length of the antenna, you need to consider this fringing effect outside of this patch antenna. So the effective length will be the C over 2 F naught epsilon effective square. So C over F naught is the wavelength, and the wavelength over a square epsilon effective is gonna be a lambda or a lambda g, and the effective wave length of the patch antenna is gonna be lambda g over 2. And you can already see the formula of the delta L, which is the extra affecting of the fringing effect for this kind of antenna. And if you wanted to see the actual length of the patch antenna, you need to see del effective minus 2 delta L. And for the ground plane, it's some rules that say for ground plane you need to add 6 times of the thickness of the patch antenna, patch dielectric, and plus L, which is the length of the patch antenna, or for the width of the ground plane you need to 6 times H plus width of the patch antenna, the patch metal. As I said, it's the fringing fields that are responsible for the radiation. Fringing fields are near the surface of the patch antenna, both in y direction and minus y direction, and since the fringing electric field take place on the edge of the microstrip antenna, it adds up in phase and produces some radiation of the microstrip antenna. You can exactly see the fringing fields and fringing effect on the right hand figures, and you can see in this figure that this fringing effect responsible for the radiation of exactly radiation of the patch antenna. So if you change the W, which is the width of the patch antenna, you change the propagation constant, which you change the input impedance of the patch antenna. So if you change the L, because it's a kind of resonator, you change the frequency of this resonator, and by changing the L you are producing the frequency, and by changing the W you change the propagation, which is related to input impedance. As I said before here, the patch antenna can be act as an open circuit transmission line, and the voltage reflection coefficient will be 1 here, and the voltage and current are out of phase. So at the end of the patch antenna, voltage is in their maximum, let's say plus V, and at the start point of the patch antenna and half wavelength away, which is the length of the L, half wavelength, at this point the voltage must be minimum. So the fields you can see in this figure, and also you can see the fringing effect here. So as I indicated, the fringing effect causes the dimensions to look slightly bigger than what you see in the metal. Here you can see the microstrip patch antenna, which feed with a microstrip transmission line over the substrate, and see the pattern in E field and H field. And this is the radiation pattern for a square patch antenna, which is equal to half of the wavelength. There is a different feeding structure in a microstrip patch antenna. Usually the input impedance of the patch antenna is usually around the 300 ohm, so you need some transformation to transform the 300 or 200 ohms to 50 ohm to match with your coaxial line or your feeding network. So there are some feeding network structures, and there are some options here you can choose based on your applications. First of all, it's microstrip transmission line feeding. As you can see, the idea of this kind of structures for the feeding network is to move the feeding point to the somewhere near the center, and create a sinusoidal distribution of the current, and the current increase as we move away from the end. So also the voltage also decrease. So you can see the input impedance of this at the point of the R has a cosine square of PR over L and input impedance at the 0 point here, which is the start of the microstrip patch antenna. You can see this kind of gap, which help to transform the input impedance of the microstrip antenna to 50 ohm. You can model this gap with L and see if you can, if you model the whole structure, and the input impedance of this microstrip antenna can be transformed to the 50 ohm. This kind of structure are very common to design a microstrip patch antenna. Also, you can see the coaxial feeding. The location can be modified in a similar manner of the inset feeding. You can see the feeding goes through the patch antenna, and by this way you can decrease or reduce the undesirable radiation from the feed. And there is based on your application, you can decide you have the microstrip feeding or coaxial cable feeding based on your application. And because you don't have your undesirable radiation from your microstrip patch feeding, so this kind of antenna is gonna be more accurate and more acceptable for array antenna. Also, if there is some aperture feeding, strip line or aperture feeding, there is some trade-off between the antenna and feeding network, especially in the microstrip antenna and microstrip line, because for microstrip line we are interested to use a high permittivity to reduce the losses and spurious radiation. But for designing a patch antenna, microstrip patch antenna, we are interested to have a low substrate permittivity. There is a trade-off between them, and this kind of a structure increases the fabrication difficulty because it's a two-layer PCB and difficulty to fabricate it. I think the advantages of this aperture feeding, it can be reduce the undesired radiation of the feeding network, which this feeding structure is shielded from the antenna. So this design structure are gonna use in large array structures like in phase array antenna or in 5G or satellite communication antenna, which you need to have the 100 or 1000 elements of array antenna, and it's gonna be something difficult to manage the feeding structures or to handle the perturbation of the radiation of the feed on other element. So these structures are very common in a large array antenna. There's something more complex feeding design like a strip line or something like that. You have your foam, your air, your coaxial feed, your patch antenna. There are many design, complex feeding design, which you can find in literature of the patch antenna. And now we are gonna to design example. We're gonna we're gonna go to the HFSS and see the how to design the microstrip antenna in 10 gigahertz with FR4 dielectric, which relative permittivity of the FR4 substrate is 4.4 and the dielectric loss tangent is 0.02. So it's a little bit different from this structure. By the way, we're going to see how the result and what see this one of the antenna after the post-processing the impedance normalization. So and see the input impedance, and you can see the resonance frequency where the imaginary part of the input impedance gonna be 0 and the real part of the impedance gonna be maximum. In this design we see the two, especially the two resonance, which you can see it, the main resonance occur at 10 GHz, but another one occur at 12.5. You can see the radiation pattern. The directivity is going to 5 to 7 dB, as you can see here, and we move on to the HFSS and see the radiation pattern. It's in a E plane of the antenna. We're gonna see the H plane. If you see the H plane, you can see the side lobe of the patch antenna. And for the phase array antenna or in array antenna, it's better to have to decrease the side lobe. There is some techniques and there is some complex structures that gonna decrease the side lobe level of the antenna, which is very critical in phase array antenna or in satellite communication exactly, or in 5G application, to have the side lobe level below the minus 30 dB, minus 40 dB, and something like that. So let's move on to HFSS. So let's move on to the HFSS and design a microsweep antenna. Create a substrate. The position will be minus sub x divided by 2 minus sub y divided by 2 and 0. X size will be let's say 15 millimeter, and again let's say 15 millimeter. X size will be sub x, y size will be sub y, and z size will be h, which is the height of the substrate. Gonna be 1 millimeter. So let's assign a material. Let's say FR for epoxy 4.4, and let's see the patch antenna. For patch we need to again what 2 means patch box 1 say sub AC patch minus X patch minus Y patch over 2 and H sub. So let's say for 10 gigahertz the lambda is going to be 30 millimeter, and lambda over 2 is gonna be 15 millimeter, but the substrate permittivity epsilon effective is gonna be 4.4, and the x is gonna be lambda over a square of epsilon effective, or epsilon r, which is about a lambda over 4. So let's indicate the length of the patch is gonna be 7.5 millimeter. Again, it's a square patch. X size will going to be xp, yp, and the thickness of the metal, let's say thick, it's gonna be 0.07 millimeter, which is a 17 micrometer or 35 micrometer. There is a two order that PCB manufacturers allow us to design our antenna or our board, our PCB board. So we'll create it and assign a boundary to patch. Let's say PEC. And now for fitting a structure, again, let's just we want to show how the microstrip line or microstrip patch antenna works. So, and we don't even want to complete the microstrip line, just we want to see how this dimension works. So let's say have some small microstrip line which align or assign to this patch, microstrip patch. For this, let's say we are in a minus xp over 2 and minus wl, which is the width of the microstrip line divided over 2 and inner edge sub. Again, we should create a comma here. Okay. So let's say 1 millimeter for the width of the microstrip line. We're gonna change it and optimize it. And let's say for x, let's say again minus 1 millimeter. It's okay. Just we wanna see how to this patch antenna radiate. WL for the y and the thickness of the, okay, we can here see our microstrip line. It's gonna be little wide, but I think it's okay. We can change it. We can go to the HFSS design properties and change WL to minus 0.5. Okay, it's gonna be okay right now. So now we wanted to assign excitation. Let's say we are in a YZ plane and create some planar sheet. Okay, define it. So minus WL over 2 and from 0 here in the minus xp over 2 minus 1 millimeter. In orientation x, equal size gonna be omega a and wl, sorry, y size h sub. Right, okay. You can see the excitation port, we're gonna excite a LAN port to it, assign excitation, LAN port. So next, new line for integration. As you remember, going to the middle to middle, here to here. We just noticed that we shouldn't go. Just note that we have to go to just notice that we don't need to contact the PEC. So is the as you can see here is under the PEC, under our macrostrip line, because our LAN port shouldn't contact with any PEC or conductive material. 50 ohm, yes. Now we should assign an excitation, assign a boundaries, care for your boundary. There is another way, create a region, you can offset it, but okay. As you can see, you can create a region by setting a percentage offset for X direction, Y direction, or Z direction to create a box of your object. So let's say 10%, 30%, 100%. And just for individual, okay, 60%. Just for the radiation side, we're gonna use like 3000% because we need to create a box large in this direction. Okay, yes, 300 is gonna be something. Can change it. Okay, it's gonna be okay. And can boundary assign a boundary radiation pattern, radiation box to this, and see the radiation box here. Okay, and what we forget to create a ground. We forget to create a ground. So let's have a box for ground, which is big. Oh, it's gonna be PEC. For box 1, let's assign material PEC. For feeding structures, for this again, we're gonna assign PEC. minus sub x minus sub y divided by 2 and 0 sub x for y size sub y for z size minus tick. You can see the box, the ground plane here. So what we need to validate it, or we need to analyze the setup. So let's add a solution setup at 10 gigahertz, 10 pass, going to be 32, safe field at 10 gigahertz. That's gonna be okay. So we validate and write. After running the simulation, we're going to the result. I'll create a parameter for real and imaginary part, and you can see there's a little bit different to 10 gigahertz. I know, because the fringing effect and the delta effective now, and by putting some mark here, you can see at 8.4 if we have some resonance frequency. By changing the length of the patch of the antenna, we can move the resonance to 10 gigahertz. By the way, if you see, it's about a 300 ohm, the input impedance at 8.4. If you post-processing the excitation for the 300 ohm, you can see the S11 is minus 30 at this frequency. So let's see the radiation. I forgot to insert a far field setup. Let's have a minus 5 direction, minus 180, and a 5 decrease step. And the frequency of the 8.4, we change the analysis setup to see the radiation pattern. Okay, let's run the simulation again. Okay, there is a little bit difference, but again, for the so you can see at 8.5 we have a resonance, and let's see the radiation pattern going to the results, far field plot, and you can see the 3D plot, the gain total with dB. Okay, you can see the microstrip patch antenna pattern here. Also, we can go to the structural view and see the radiation pattern with the transparency of the 0.6. You can see the radiation pattern of the microstrip patch antenna on the bore side of the antenna, and if we scale 1 to these structures, you can see the holder, power holder, radiation field going in front of both sides of the antenna, and there is a little bit the behind of the antenna. If you can see the 2D plots of this at y equal to 0, you can see the plot should be in dB. You can see the microstrip pattern and the gain, and because of I think something wrong with it, because it's gonna be, for the next session we're gonna work on the gain, and for next session we're gonna work on the array of the patch antenna, and work on how to improve the gain and directivity of the antenna, or how to decrease the side loop level, and how to create a grating loop, how to reduce the creating a grating loop, which is not desired for us to radiate in a microstrip patch antenna.